I think that we are now ready to start. We have almost 65 people connected. So first of all, welcome everyone to this webinar. Today's title is Community Hazard Risk Assessment Tools, Structural Fragility and Vulnerability and Reliability Systems. This webinar is part of the UNESCO Chair on Disaster Risk Reduction and Resilience Engineering webinar series. My name is Rafael Fernandez. I work as a research fellow with the UNESCO Chair at UCL. And today we are very glad to have Dr. Asana Paramalbateri and Dr. Ji Young from the University of Glasgow. So just to introduce our speakers today, Dr. Asana Paramalbateri is also a postdoctoral research fellow at the UNESCO Chair. She works mainly on tools for disaster resilience of integrated systems. She works in particular with the integration of variation networks and agent-based modeling. And her research has been focused mainly on confined masonry and school infrastructure. Dr. Asana is also working in the Mediate project, the Resilience of Infrastructure Systems on the Horizon Europe project, and she has worked in different consultancy projects across the world. We also have here Dr. Ji Young. She's a lecturer in smart, sustainable, and resilient infrastructure at the Division of Infrastructure and Environment and Glasgow Computational Engineering Center in the University of Glasgow. She works mainly on reliability systems and reliability-based optimization of the structural and infrastructure systems against extreme events, and in particular natural and human-made hazards. And she is particularly interested in all the analysis related to complex and large-scale systems, including transportation networks, utilities, resource systems, and structural systems. So for today, we have the first session of these 2 days course. The first day, today we will talk about technical background. So the first part will be mainly focused on fragility and vulnerability assessment, and the second part on the network reliability assessment. And tomorrow we will have the hands-on tutorial. So we invite you also to join tomorrow at the same hour to continue and to use the different tools that will be shown in the next few hours. So without further ado, Asana, please go ahead, and thank you again both for joining.
Asana, you're muted.
There was a question.
Hello. Sorry. Yeah.
There was a question that they couldn't hear properly. So, Asana, please try to your.
Okay. Are you able to see my screen?
Yes, we are.
Okay.
But it's not in presentation.
Okay.
No, this one is the presenter mode.
Yeah. Is it okay now?
Yes, it is.
Okay. Sorry about this. Always. Thank you all for joining, and welcome to this session. Thank you, Rafa, for the kind introduction. In this session, we are going to look at some tools for community hazard risk assessment. We will start with structural fragility and vulnerability in the first part, introducing some tools for assessing the structural fragility and vulnerability. And then we will move on to the system reliability. So we are looking at systems of education infrastructure where education settings such as schools and the road networks that connects the schools with the communities and between themselves. These are often faced with hazards, and we will look at the tools for risk assessment in this presentation. So this is a case study based in Philippines in the Cagayan de Oro, we will be basing our data and assessment on the school buildings in Cagayan city. As we understand, it's about 70% of the school building stock comprised of reinforced concrete buildings, and others are light steel, sorry for the spelling here, light steel frame with masonry and other typologies. So why we are looking at specifically education resilience is mainly because of it's a fundamental right for every child to have access to quality education, as we also see in one of the Sustainable Development Goals. And it's one of the main objectives of the UNESCO Chair to promote resources for education resilience, risk assessment, and recovery. We thank our colleagues in Xavier University, Philippines, who have been an integral part of all of this work in Philippines, starting from the data collection on schools and the road networks, and also with the recent workshop and event we did in the Cagayan de Oro, with the support from a PR seed grant. Now, we come to the topic of today. What we understand as the risk from natural hazards is often comprised of overlap of a spatial and temporal overlap of three components: the hazards, exposure, and vulnerability. So for the hazard characterization, we use models that characterize the likelihood of experiencing different hazard intensities at different locations. For the exposure, we understand the location, the quantity, and the physical characteristics of our assets, which are exposed to the hazards. And the third component is the likelihood of damage to these assets under different levels of hazard intensities. So in today's presentation, we are going to look mostly at the earthquake, hazard, exposure, and vulnerability, even though the techniques in general could be extended to other hazard types. So how do we begin with such an assessment of risk from these three components? Starting with the hazard, we use existing or pre-developed hazard models, such as the case here for the Philippines. It's a country that is exposed to several different kinds of hazards, where the hazard maps such as this, they provide the likelihood of exceeding certain hazard intensities with the given return periods and the regional variation. Coming to the structural assessment of our exposed infrastructure, we are talking about schools here. So within the city, we will have the assets placed in distributed within the city. So we first identify certain number of representative index buildings in order to reduce the load for analysis and also to make the problem quantifiable and handling. We are able to handle the size. So for this, we will introduce certain tools, following which we can identify some of the representative buildings, which can be then taken up for detailed seismic analysis, where you would quantify your capacity of your buildings in terms of their base shear and displacement capacities. With the from the analysis, we will then move on to the quantifying the seismic performance in terms of seismic fragility, which is usually used to express the probability that a level of damage is either reached or exceeded for a given intensity measure. And from fragility, we can then move on to vulnerability, which quantifies the likelihood of losses under a range of hazard intensities. So these inputs are based on the structural assessment of the school buildings in our portfolio of buildings, which can then contribute to the system assessment, where we also also integrate this interdependency and interaction between different elements, such as the school buildings, the road networks, the community that uses both these assets. So without further ado, we will just focus on the structural assessment in this part of the presentation. And we will introduce first the glossy taxonomy, which is a tool for identifying representative index buildings from a large number of building portfolios for schools. Secondly, to derive the fragility functions from the capacity curves of the buildings, we will use the N2 method and introduce an Excel-based tool for deriving the performance points from the capacity curves, following which we will go to a least square regression tool for deriving the fragility parameters, and then a last tool for converting the fragility functions to the vulnerability functions. So we have already sent you an email with resources for performing all of these functions. We understand that there are also more people registered after the email, so we will send a fresh set of emails this evening after the session. So we will first focus on the exposure characterization using the glossy approach. So GLOSSY is part of the Global Program for Safer Schools, an initiative by World Bank with UCL and UniAndis, where school infrastructure has been characterized in several countries, and a global baseline of school infrastructure is produced. So this is the global baseline basically provides the information on impact of natural hazards, natural disasters on school infrastructure, and also the communities. So it's not just the buildings that are of importance or concern here, it's also the exposure of children in the schools. So the second component of the GPSS program is the GLOSSY, which is the Global Library of School Infrastructure, which provides the tools for identifying the characteristic buildings or index buildings, and also to derive the fragility and vulnerability functions. So the idea of this presentation is not to give a complete tutorial or complete presentation on GLOSSY. We refer you to a previous course of UNESCO Chair dedicated only to GLOSSY application with several examples and tutorials. You can use this link to go to the website. And also we have all our previous courses recorded on the website for your reference. This website sorry, if I can go to on the World Bank as well. This is a useful resource for you to get much more detailed information on GLOSSY, and also see the global baseline. And the library. So here we see the catalog of building types, the taxonomy itself, its development, and vulnerability quantification. So within the typologies and catalog of building types, you are able to see identified school building types, both in the load-bearing masonry typology and also reinforced concrete typology. So we will come to this again as we discuss the fragility and vulnerability. Coming to this GLOSSY taxonomy, it's a 12 parameter based approach to characterize seismic performance of each and every school building typology. So here we look at these 12 parameters a bit more in detail. However, we will focus our efforts on the first three, which are the main structural system, height range, and seismic design level. And most of these parameters are observable or gathered through visual surveys in the field, visiting the school buildings and gathering the information. So as I said, the parameters in the GLOSSY are listed here. The first three are called the primary parameters, which define the main structural type, the building type. Within the main structural system, GLOSSY currently focuses on two types of structures, the load-bearing masonry and the RC, reinforced concrete structures. We will look a bit more into each of the primary structural typologies in the coming slides. The rest of the parameters, for example, the height range, is fairly straightforward. We identify if the building is a low-rise, mid-rise, or high-rise structure, which has a bearing, which has an influence on the period of the structure and its seismic performance. Similarly, seismic design level, this varies between typologies. Seismic design level is characterized to poor, low, medium, or high design categories based on based on their seismic resistance features. So we will look a bit more detail about this as well. Similarly, all of these parameters, some are very visually observable, while something more say, for example, the foundation type, it may not be directly observable, for which we would require some more additional information. And some of the parameters which are defined differently for the two types of structures, say the load-bearing masonry and RC. So because we saw that at least 70% of the buildings in the case study database are RC structures, we will focus this presentation on RC typologies. So here we have the five subclassification of the RC main structural system. The first one is the RC frame without infills, the bare RC frames. It might also include the RC frames with light infills, which are not structural. The second RC2 is the frame with infill walls. RC3 is the RC frames with infill walls and also the short column effect. So this is a very common feature in school buildings where we have the provision for windows and then leaving sections of the columns, small sections of the column unsupported and attracting more damage than the rest of the locations. The fourth one, RC4, is RC combined with additional lateral resistance systems such as the braces. And the fifth and the last category is non-engineered and non-conforming structures, which we see all over the world and which are probably more vulnerable to earthquakes. Similarly, we have a distribution of typologies within masonry, depending on the type of masonry unit and mortar, different types of unreinforced masonry, and also better seismically performing structures such as the confined masonry, reinforced masonry, or steel framed with, again, load-bearing masonry walls. So as I mentioned, the seismic design level, the third category, the third parameter, it depends on several factors, and it's not a very straightforward distinction between what is a poor or low design. We need to have the information on a slightly more information than a visual survey. So this is often collected from the building year, the year the building is built, and the kind of seismic code that conforms to. If none of this is available, we can then look at minimum dimensions in structural elements. For example, what can be called a low design as opposed to a high design. And also, if we have information on the stirrup spacing and the kind of ductile and fragile behavior, collapse mechanisms that are expected. So this is in the case of reinforced concrete frames structures. The fourth parameter, we said the diaphragm type, which has an influence on the seismic performance of the building. In the case of flexible diaphragms, we do not expect the diaphragm to have much lateral stiffness to equally or proportionately distribute the lateral loads to the walls, as opposed to the rigid diaphragms, and hence making the flexible diaphragms prone to more local failures. The span or wall length, the fifth parameter, is defined again differently for the masonry and RC cases. And in the case of RC, we can call any span more than 6 meters as a long span, anything less than 6 as a short span. So this again has influence on the way the frame is going to behave under lateral action. So the next parameter, the wall opening length, this is again something that varies very, very significantly between masonry and RC. So within the masonry, we have different distinction between the confined masonry and unreinforced masonry types. For the case of RC, this is characterized as pier type or the column type, where you can have a regular column or a weak column, regular or strong column, where we have at least the column depths equal to or greater than the beam depth. The kind of foundation type not just depends only on the foundations, it actually influenced it's also influenced by the kind of soil the foundation sits in. So we can have this kind of combinations where a foundation can be classified as a stiff or flexible. Say, for example, you have any kind of strip footing, which is often seen in the case of masonry buildings. Sitting on any soil can be classified as flexible foundation, while other concrete footing kind of foundations can be either flexible or stiff, depending on what kind of soil it sits in. So the next parameter is seismic pounding risk. It's not an issue with the structure itself, but because of its proximity to the adjacent structure, which then becomes a problem under a seismic action. The 10th parameter is the seismic retrofitting. So we identify if it's an original structure or a retrofitted structure with significant improvement in seismic performance. The next one is the poor or fair or good conditions, which is generally observable from visual surveys. In the case of RC structures, for example, there is spalling, corrosion, or reinforcement being visible. Or in the case of concrete itself, there could be honeycombing or poor aggregate grading and so on. So the last component or the parameter is the vulnerable component, specific non-structural vulnerable components. So these are not really structural elements, but their failure can cause damage to death or it can cost money. So this is, for example, things like parapets or ceilings or infills and tiles and so on. So how these are significant is when we identify the typologies for the main first 3 parameters, we identify the building types, and for the remaining 9 parameters, we identify specific categories within the first 3. So we gather the information from site using forms such as this, information on 12 parameters, although we may have to collect more information, for example, the year of construction or the or more information that would then lead to the decision on seismic design level, for example. And there is more information and guidance available on the website that I showed you earlier on how to apply the taxonomy, and also a complete guide into all of these parameters for both RC and masonry. So we invite you to check these resources if you're interested in really applying the taxonomy in your cases, in your research or work. And also check the UNESCO Chair's course on Glossy for more details. So here, if we look at an example application, you see an RC school building here with 2 stories, 2 floors. First, you check the moment resisting frames here with isolated infill walls. You can see that it's a mid-rise 2-story building with some information available on the design level. So we know that its stirrup spacing is within D/4, and we know that the minimum dimensions are more than 30 centimeters. So hence we expect ductile collapse mechanism and assign high design. And other parameters, say, for example, irregularities. This is, again, it can have a horizontal, vertical, or both kinds of irregularities. The spans, short span or long span, the kind of foundation, and no pounding because the structure is standing on its own. Original structure without retrofitting. There is no, visually it looks like well-maintained, good condition building. And oftentimes we take a look inside the building to see the features of regular column or the type of diaphragms, the rigid diaphragm in this case, and also for non-structural vulnerable elements that are present in the classroom. So combining all of these alphanumeric values or the codes, we generate the taxonomy string. So for this building, we get this RC1 MRHD, the string that really is a DNA of this building. So once we gather this string, we can then produce the string for every building in our population or the portfolio to identify the most representative buildings for this, for the analysis. So this is an example with confined masonry. Similarly, you can identify the main structural system. You have masonry buildings confined with RC elements. It's a low-rise building. We understand it's a poor design because it has minimum required confinement present, but not additional confinement. Similarly, we have flexible diaphragm, no irregularities, long panels. In the case of masonry, the panel length is different from the RC, which qualifies it as a long panel. Similarly, flexible foundations and large openings without confinement. From outside, you can say that the building has no pounding risk, there's no evidence of retrofitting, and it has good conditions. But this has a ceiling that is a known structural vulnerable component. So for this building, we generate a string in this form. Some examples from our Kageyantoro database. This is a RC HR high-rise building, which is identified to have a medium design level. This is another building with 2 stories, a mid-rise RC2 building. So if we continue this as exercise for the entire population of buildings we have, we can then produce this kind of distribution, identifying the most recurring typologies and most vulnerable typologies, which can then directly and immediately inform our decisions to intervene. So without considering the 9 secondary parameters, we can stick to the first 3 to identify the main structural or building types, and then assign fragility functions which are available from the World Bank database if you can find similar or comparable typologies to this typology. So please watch out for the website that I shared before, the GLOSY website, for updates on the fragility functions that are available. The website is being updated and migrated to a different platform. So currently the fragility functions are not available, but you will be able to see them once the migration is complete. So as I mentioned, this is where you will find the typologies, find the index buildings. And if you go to each one of them, you will be able to find more information on them and the fragility function that is corresponding to this typology. So if we move on to the next section, oh, sorry. Suppose we don't have a typology that is representative of our buildings on the website, or any database of fragility functions that that you have access to. We might then end up having to derive these fragility functions for our buildings. So we can have different approaches of deriving fragility functions, for example, analytical seismic assessment methods, or empirical fragility derivations based on existing data of damage after earthquakes. So here we are going to look at the analytical approach to fragility and vulnerability. Again, the attempt here is not to entirely give a presentation on deriving fragility functions in this talk. We refer you to a previous course on the UNESCO chair again in this regard, for which the recordings are also available for your reference. So fragility functions, as we mentioned earlier, they express the probability that a level of damage will occur as a function of the value of hazard intensity. So again, from the fragility functions, we can then go on to the vulnerability, where the likelihood of losses from each damage state at a given intensity level is accumulated. to assess what is the total loss at a given intensity level. So there are guidelines such as the global earthquake model, which guide you through a step-by-step procedures to derive analytical fragility and vulnerability functions. So it adopts a step-by-step process such as shown here. The first step of identifying index buildings, we have already gone through this with the glossy approach, and you end up with these kind of representative index buildings for the population of buildings we have. Secondly, we can define the type of models we want to create. There are options. Again, the GEM guidelines gives choices of different model types depending on the complexity and the level of computational effort and the expertise of the person using these. So we can go from very detailed multi-degree of freedom system models to single degree of freedom simplified equivalent 1D models. So the more detailed your models are, the better, or the more closer to realistic real behavior that you are able to generate. So once you have decided on what kind of models we want to generate, we can then perform an analysis and observe the seismic performance or the behavior of the building. Again, we are not going to deal with the details of modeling and analysis in this course. With the UNESCO chair, we have a previous course on using OpenSea's platform for modeling and analysis for you to refer if interested. The next step, after we identify the model types, we need to define the damage states. So what is the level of performance you would expect or you would want the building to have is defined through the damage states. Say, for example, the FEMA guidelines that gives you 4 performance levels where the building will stay functional or building is expected to be reasonably usable and operational immediately after the event. Or the life safety limit says the building is damageable. It suffers damage, but there is no threat to life safety. And the last one, the collapse prevention level, it suggests that the building is expected to be stable under gravity loads while suffering extensive structural damage. So this is often defined in terms of an engineering demand parameter. Oftentimes we use the roof displacement or interstory drift values to characterize the engineering demand parameter, and the limits are defined as drift values on the capacity curve. So also the FEMA guidelines, it gives you a detailed explanation on how we can identify the building has reached immediate or each of the damage states or performance levels through minor cracking on primary elements to extensive damage to beams. For example, for the life safety and for the collapse prevention, you see extensive cracking and hinge formation in RC buildings, RC frames. So with the damage states defined, we can then go on to do the analysis type. We can, similar to the case of choosing the model types, we can go for very detailed nonlinear dynamic methods or go for very simplified mechanical models that are less computationally expensive. So again, this depends on the complexity of computation, the available resources, and expertise. In this method, for example, the pushover curve is a nonlinear static method where we would create a structural model and subject it to gradually incremental lateral load to produce a base shear versus rooftop displacement function. So this characterizes the nonlinear capacity of our model. So once we have the capacity defined or characterized through the pushover curve, how do we go to fragility functions? So this method here, we would first idealize that pushover curve into a bilinear curve. If you have a multi-degree of freedom model, MDOF model, we would first reduce it to a SDOF model and then convert that to a spectral space. So we bring our capacity to the ADRS, acceleration displacement spectrum space, which can then have a direct comparison between your seismic demand in the same space. So the blue curve here is recorded ground motion, which is reduced or which is modified to the inelastic spectrum, which is also dependent on the properties of our structure. So this gives us a performance point where our building capacity meets the seismic demand in the inelastic space. So this particular point is obtained as a performance point, which can be repeated for a number of ground motions to generate a cloud of performance points. This method is called N2 method, which is widely used by practitioners and the engineering codes. So we have implemented this N2 method on an Excel-based platform. We will first see what inputs we require for running the N2 method. So what you are looking for is you have already performed your model analysis to produce a pushover curve where you have characterized what is the base shear versus roof displacement relationship. So you are given with, if you can see the screen still, you are given this input file, which is the MDOF capacity curve. And other information you would need is your number of stories, the story height, the mass and mode shapes of the structure. The remaining parameters, the fragility derivation, vulnerability derivation, we will discuss as we talk about these. So once you have this input file, you can then go to the N2 method bilinear capacity curve tool. The first one here is based on an intensity measure of spectral acceleration, while the second one is the PGA, the peak ground acceleration, which is often useful for masonry or confined masonry buildings. So if you go to the N2 method toolbox here, you have 4 tabs, where first one, the input structural data, where you will paste the capacity curve that we just saw in the input file. So if you paste your capacity curve values here, along with the other information, that is the story height, the number of stories, mass of floor 1 and 2, and the mode shapes. So, and the one other parameter you can play with is the percentage of the ultimate capacity, which is for the idealization. So the blue curve here is your original curve, which is then idealized as the orange curve here. So this already produces our SDOF, equivalent SDOF capacity curve from the MDOF capacity curve that we have inserted. So with this first tab, that characterizes everything to do with our capacity. The second tab here is the host of input ground motions, which is a FEMA, as a set of ground motions, 22 ground motions from FEMA, which is then scaled by a number of factors here. Over 20 scale factors are used. So each ground motion is scaled by the scale factor here, and we perform that comparison between the capacity and the inelastic ground motion spectrum. So once you click the EDP generator here, you will see that the program runs your input files and assesses the performance points. So when you are installing or saving your tool, the N2 method tool in your system, and make sure that you enable macros so that the program is able to generate the engineering demand parameters. So the last tab here, this will give you the results of the analysis, which is basically the intensity measure versus the roof displacement. So each of the points that are generated, that are found as a result of comparing between the ground motion record and the capacity curve. So we have produced the IM versus EDP function here as a cloud of performance points. So if we go back, I think as minding the time, I will continue the talk, continue the presentation and introduce all of the talks, all of the tools. We can spend hopefully 10 minutes in the end to discuss any immediate questions. And in the end of today's presentation, I'm going to give you a set of exercises where you can try out these tools by yourself. So you will have an opportunity to use the tools by yourself in your time. And we come back tomorrow, the first half an hour or so, we will discuss the application. So you can have questions and answers in the first session tomorrow if you have any. So as I mentioned before, we have this cloud of performance points obtained from the N2 method. Now, how do we get from cloud of performance points to the fragility function? So this is a regression problem now. You have you can use any of the available regression approaches, such as the method of moments, which is simply you calculate the mean and standard deviation of your distribution, or you can go for better methods or more other methods like maximum likelihood or generalized linear models or least square method. So here for the illustration, let's look at least square method a bit more in detail. So here what we are trying to do is a piecewise regression instead of doing a regression over the entire cloud of points. So what we identify the EDP threshold, which is the damage threshold we identify for each of the damage states. So we define the damage state first as slightly damaged, moderately damaged, extensively damaged, or collapse damage. So for each of the damage thresholds, we define an EDP value. So EDP here, the engineering demand parameter here could be the rooftop displacement. So your SD could be a value of rooftop displacement, which can characterize as slight damage. So we identify the IM points such that we have at least half of the performance points below and above the threshold value. So for example, for the SD stage, SD damage threshold, we use the points that are below the yellow line and regress to obtain the parameters of the green line. So this is then can be characterized as a line with the slope A and the intercept ln B. So the parameters A and B are obtained from the regression, which can then be mapped back to the function of log normal function, which characterizes the fragility function. So the parameters of fragility function here are the alpha and beta, which are expressed in terms of A and B, which we get from the regression analysis. So this process here of finding the alpha and beta and then getting the fragility function is inserted into this tool here. This is also one of the tools that is shared with you. So if we just have a look at how we run this part of the program. This is a MATLAB based code. However, you don't need to have MATLAB on your system to run this. So you would receive a folder of this kind, the materials for distribution, and the tools will have your LSM fragility app, which is now what we are going to discuss. You already have your N2 method Excel sheets here for your reference. So
Anna, it's a bit small to see. I don't know if you can put it larger.
Okay.
For people, it will be a bit difficult.
Okay. So here, this we have already discussed in the previous slide, the N2 method for PGA-based IM capacity curve or the SA, the spectral acceleration-based capacity curve. So if we go into the LSM fragility app, you will have a presentation that guides you how to install this program on your system. So once you install the system, you can use the input file here LSM input Excel file, which is the input for your fragility derivation. So we have already identified the IMEDP performance points from the N2 method. We would take this result and paste this into the input file for the fragility derivation. So we provide the IMEDP values as the input here. You need to also provide what is the threshold values of different damage limits that you have defined. So the slight damage, moderate damage, extensive damage, collapse damage occurs at what thresholds of EDP. So the EDP here is the roof displacement, and the threshold values are inserted in meters as 0.02 meters to 0.09 meters, which is also provided in your input file. So if you go back to the first input file that we used for deriving the N2 method, you go to the second sheet here, you are also given these inputs here for fragility derivation. So we can insert your values here, the threshold values, and the vulnerability derivation is also available here. However, we have a separate tool just for the derivation of vulnerability functions. So you can either use this or the separate vulnerability function. So here for the derivation of vulnerability functions, we will come back to this a bit later because we haven't yet discussed vulnerability. So first, we will insert the inputs, close the file, save and close this input file because we are going to write the results into the same Excel file. So once you have the inputs ready, we can open the fragility vulnerability app. And then you can run for the fragility derivation. So here we have the, is this okay? Can you see? So if you do run the generate fragility function, it runs a MATLAB code in the background to generate the fragility functions. It might take a bit of time. And again, this app is currently under further modification. So we will update an updated version on the NESCOCHE website whenever it's available. So please keep an eye for this. So your fragility functions are now derived, it's ready, and you can generate the vulnerability functions along with that. So once you have complete the run of the program, you can go back to your LSM Excel file to extract your results. So the results are also available in the LSM Excel sheet, and you can take out the fragility parameters, which is the mean and standard deviation of your fragility functions corresponding to each damage state, can be extracted from here. So this is where we are so we have now come to the point where we have generated the fragility functions using the MATLAB-based code and using the inputs of performance points as we discussed. I want to point out that this is just one of the several methods that are available to derive fragility functions. You can also go for more sophisticated methods with direct nonlinear time history analysis in different forms, such as direct distinct nonlinear time history analysis, or you can use that as a multiple stripe analysis and so on. So once we have the fragility functions, we can go from fragility to vulnerability functions. So this is where we characterize different, we also bring in the economic aspects of damage to the problem. So we assign what is the cost of damage at each damage state. So say, for example, for a given IM, the building has certain probability of being in damage state 1. In each of the damage states, we have a certain probability of exceeding at that IM. So if you take out your cost associated with each level of the damage and find the cumulative cost at that IM level, you can generate the vulnerability function. So for this, we can use a last tool in our folder. If you come to this tools, you have the fragility to vulnerability converter. Which, in which now the input is the fragility function that we have derived. So from the previous analysis, we know the mean and standard deviation of the fragility functions, which is the input for this file. Once you have inserted your mean and standard deviation, it calculates the fragility functions and also the mean damage ratio and variance, which is basically plotted as the vulnerability function here. So it gives you the mean damage ratio at all IM levels, along with the variance of the vulnerability function. So and here, what is another input is the damage ratio, which is different for different damage levels. So for example, for the collapse damage state, you're assuming that the entire building needs to be replaced or repaired, as compared to when it is a slight damage state, it's only 2%. So we introduce these damage ratios as well in your input file as the third set of input information. So this can be different for different assumptions, different type of structures where each of the damage states corresponds to different levels of damage. So with that, I think we have discussed all our, or we have discussed all our tools for deriving fragility and vulnerability functions. We apply this to an example case. You're given an RC building here that is a 2-story building with certain element of short columns, as you can see from the figure. The first input is your pushover curve, where you have the base shear versus displacement connection relation. It's idealized into an SDF curve. We then carried out the pushover to EDP's analysis using the N2 method, and then go to the fragility and vulnerability derivation. So this is the whole process of going from identifying a structure and an index building to its fragility and vulnerability. In terms of, so far we have discussed the school building infrastructure, school building inventory that we have. Another important component of the system level assessment is the road network, especially the bridges, flyovers, and overpasses, which can be damaged, which can get damaged in an earthquake event, making the connections between schools impossible, and basically the education delivery cannot cannot be achieved. So to understand how this affects the system reliability, we also characterize the fragility of the transportation infrastructure in the similar manner as we did for the building. So for each of the bridge structures, we identify the typology as we did before with available information on bridge typologies, and utilize available fragility functions that are available from literature for each of the building types. So this is, again, there are techniques and approaches for deriving fragility functions in similar manner for the bridge typologies. Oftentimes it can be a combination of different components, a bridge itself. So there are different methods of, again, deriving fragility functions, which we are not going to deal in this presentation. Instead, we use fragility functions which are available for these bridge types. So with that, the structural assessment is complete. We have generated the fragility functions, which would then be move to the system reliability model as the input functions. So in the next presentation, we will look at the system reliability approaches, but I think we have at least 3 minutes. If anybody has any quick questions, we can take, and we can definitely have a more detailed Q&A for the for any of these sections tomorrow when we come back with the hands-on task. I don't know if we have any questions in the Q&A.
I think the last question is relevant.
There are a couple of questions. Yes, Sana.
Okay.
One is how we can determine the EDP associated with each damage state.
Mm-hmm.
And
Okay.
the other one is, based on your experience, could you kindly share your insight on any available comparison between the EMS damage states medians and the IM corresponding to code-based performance level or NTC18 based ones? So how do you go from the MS98 damage state to the analytical drift, basically?
Mm-hmm.
I mean, when we have the fragility curves and want to move to code-based evaluations, yes.
Mm-hmm.
I think maybe these are best answered in writing. Maybe you can answer them here on the. You can type the answer YG because it will
Yeah,
take
I can talk.
2
Yeah.
minutes.
Yeah, I think basically this first question, how can we determine the EDP, is answered by the last question in some extent. So you can get the EDPs from any of these guidelines, the EMS or even FEMA. You can get for different damage, different building types. There are available damage thresholds which correspond to each of the damage state or performance levels. But however, in our experience, sometimes you will still have to like perform your own analysis and correspond and find what is the EDP corresponding to damage level. For example, in confined masonry, where and another method is to actually look in the literature. So we can gather several experimental or analytical analysis to then have an analysis of what kind of EDP corresponds to what kind of damage state. So I think that's what has been our approach. I think, yeah, like Dina suggested, we can move on to the next presentation, and then I can take the questions offline.
Okay, thanks.
I will stop the presentation and
I'll share my screen.
Yes, you have several questions open now, Sana, that you can answer to. I'm sorry I have to leave, but thank you very much, June, for providing the follow-up hours.
Thanks. Yeah, sure. See you. So I will start the second part of this tutorial session, which will be about system risk assessment, especially those systems with discrete state components. So I will first briefly lay out the basic problems that we'll be considering for today and tomorrow. So when we think about our infrastructure systems, then our infrastructure assets, then there are schools and bridges, and they are subject to some hazard risks, then we face these uncertainties from everywhere. And if we zoom into one of these core systems, then we discover that this is actually a system of multiple components. In this case, this core complex is a system of multiple buildings. And always the challenge is how we can correctly decide the uncertainty or the probability distribution associated with system probability, system event, which is determined by the uncertainties in the component probabilities. So for instance, in this case, there are 14 buildings that each have their own probabilities for each demi-state, and how they are all combined with the system function to decide the uncertainty in the system event. And this is what we're gonna discuss during the rest of today, where using system risk assessment tools. So this on today, this was the brief background of the system we are considering. And first, I will introduce the formalized definition of system risk method or system reliability problems. And there are two commonly adopted methods, sampling and decomposition. And we will go over a brief overview of these two methods. But in this tutorial, we're gonna especially focus on this decomposition method. And I will introduce how we can use MBNpy Python package to implement this decomposition for the decomposition for system risk assessment. And on tomorrow, we are going to run a hands-on tutorial by looking at the codes together to assess the risk of school complexes in the case study area, Cagayan de Oro, the Philippines, that Asuna just showed with the community that we work together. And at the end of the tutorial, the intended learning outcome is first, you will be available to understand the concept of system risk assessment, and you will be able to analyze your own system risk problems using MBNpy module. So I will first start with the mathematical representation of system reliability method. So always we are given some component probabilities, and these components come with some probabilities with each of their dummy states. And they are combined with a system function, which is often deterministic. So they take some state of these component events. We often call it component vector state. And then it returns a system state, which is often failure and survival. And this leads to the system, and we call them system reliability analysis. And mathematically, this system failure probability, which is the same as 1 minus system reliability, is computed as the summation of the probabilities of each possible combinations for those combinations that lead to system failure. So this is the equation that we will be solving during this tutorial. And the challenge arises from this the necessity to go over each possible combinations, because the number exponentially increases with the number of components, as we will see repeatedly during this presentation. So I will briefly illustrate a toy example so that it makes more sense to you. So if we have this system, And we are interested in the connectivity probability from N1 to N3. And we have these three components that represent each of these three edges. And the probability of this first component to fail is 10%, the second 20%, and the third 30%. And then now to calculate the failure probability of this system, we need to go over each combination. So first we start from the combination where all of these components survive. And by the way, during the rest of this presentation, I will use this simple expression for this to represent this assignment that where the superscript represents the assigned state to this particular random variable. So here we have all these three components that take the state of 1. And if we run a connectivity analysis with all these edges present, then we get the system survival. And the probability of this joint state, this component vector state, is if we assume a statistical independence, then we have this x1 being 1 as 90%, and the x2 being survived 80% and 70%. So we have this around 50% of this component vector state happening. And we move on to the next combination, and this time x3 fails. And so without this the third edge, the two nodes are still connected. So we conclude that it is system survival. And now we modify this probability to failure probability, and we get around 20%. And we go on, and if we reach this combination where now the first edge fails, then without this edge, the two nodes are disconnected. And we get this the probability of this component vector state, then we have around the 6%. And we continue this process for all of these 8 combinations, and we find that these 5 states lead to system failure. So we sum up all these probabilities for these failure cases, and we get around 50% of system failure. So this is what we mean by this formulation, where we find those combinations that lead to system failure, and we sum up their probabilities. Then, of course, the challenge is now we have these possible combinations in an exponential order of the number of components. And this is problematic because if we have 100 binary state components, which are not too many considering real-world systems, then we already end up with an impossible number. So solutions have been developed not to enumerate all these instances, but to find the bypass while we get accurate enough results. So that will be what we'll be discussing as solutions in this tutorial. So I will first start from the sampling, which is the most common solutions. And I will introduce Monte Carlo simulation, which is the most vanilla method. But the characteristics of this sampling method are present in other advanced sampling techniques as well. So for Monte Carlo simulation, this method is brute force generation of samples by given probabilities. So if we want to calculate the failure probability of this system, then we generate samples based on the probabilities. And for each of these samples, we run a connectivity analysis and decide whether this leads to system failure or not. So in the first try, if we generate 10 samples, then we have these 4 samples that lead to system failure, or in other words, the disconnectivity between these two nodes. Then we simply get the ratio as the failure probability. So we have 4 samples out of 10. So we conclude that the failure probability is 40%. And we run another analysis, then we get no samples that lead to system failure. So we decide that the system failure probability is 0. And we run another one, then we now have this 4 another 4 samples, then we conclude that the failure probability is 40% again. But if we recall, the true failure probability was around 15%. So what's going wrong? And this is because Monte Carlo simulation needs an enough number of samples. And so we usually decide the required number of samples by using this measure of confidence, using this coefficient of variance as measure of confidence. So we have, and we have this, which is defined as the ratio between the standard deviation and the probability and the mean value of the quantity that we are estimating. And in case of in here, this quantity is the system failure probability. And this standard deviation is formulated in this way when we run Monte Carlo simulation. And since this system failure probability is usually much less than 1, then we can approximate this term to 1, and we end up having this formula. Then if we look at the required number of samples to meet a target COV, then this required number is 1 over the system failure probability, and also multiplied by the square of the target coefficient of variance. So if we are targeting 5% of COV in this case, then we need at least 2,600 samples. And so if we go on generating samples, then we can see that now the true value falls within this confidence interval. So this is how MCS achieves accuracy. Then if we analyze the complexity of a Monte Carlo simulation, then this number, the complexity, which is represented by this required number of samples, increases with a lower failure probability. So they usually suffer with systems with very low probability, which often happens with the real-world systems where safety is the most critical consideration. And if we look at the rationale behind this formula, then we can if we multiply n by this failure probability, then which becomes the number of failure samples, it becomes a function of only COV. So this means that if we are targeting 5% of COV, then this Monte Carlo simulation gets this level of confidence when it sees at least 400 failure samples. And if we have a low failure probability, then we need to generate more samples to see this number of failure samples. And this is why when we have a lower failure probability, we need more samples. And so if we are targeting 0.1% of system failure probability, which is not too low, and in terms of real world setting, and if we are targeting 5% of COV, then we already need 400,000 samples. If it takes 1 second for a system simulation, it means it takes 5 days. So, and another constraint is whenever component probabilities change, then the MCS needs to be done all over again. So this means that this is because MCS cannot reuse the previous result, and this has also been the challenge for practical implementation because component probabilities usually constantly change when we do analysis over a community. Then there's an alternative, which is the decomposition method. And the decomposition method achieves its computation efficiency by using the understandings of a system event. So in our case, the solution that we are going to look at utilizes this coherency. So it applies to only coherent systems where better component states do not worsen the system state, which is very common in many system simulation functions, including many of these network analysis functions. So, the basic idea is that in the decomposition method, if we have a sample that we know that this is system failure, then we instantly conclude that the domain that is worse than this sample also belongs to system failure. And if we identify a sample that belongs to system survival, then we can instantly identify that the domain that is better than this state already leads to system failure. And we can continue this process until we identify enough system domain. And in case of Monte Carlo simulation or other sampling methods, even if we know about these samples, we still need to sample the other parts that can be inferred from the stage of these samples. And this is how this decomposition method achieves its efficiency. So then let's take a look at how this works. So we have this, let's consider this problem where the xn, these edges, 5 edges take the state of either 0 and 1. And the system failure is defined as this connectivity between N1 and the N4. Then we start from this total event space, and we start from this this variable, and we branch this total event by failing and surviving. And if we look at this branch, then now we look at x2. And we now find that if x1 and x2 fail together, then the system fails with this minimal failure conditions, where if x1 and x2 fail together, then the system fails regardless of the state of the other components. And if we go on branching this branch, then now we have this x5 and now if x2 and x5 survive together, then the two nodes are already connected regardless of the other component state, so this system survives. And for this branch, if we look at x3, then if x1 and x3 and x5 fail together, then this branch belongs to the system failure domain. And if we look at x4, then depending on the state, we conclude it is either failure or survival. And we can continue this process for other branches as well. Then now we reduced this complexity from being exponential to the number of components to the number of branches, in which case there are 10 branches. And we also found these 4 survival rules and 4 failure rules that we can use for risk management. And once we are done with the decomposition, then calculating the system failure probability is easy, because we can simply sum up the probabilities of these failure branches. So if we have, for instance, the component probabilities as the 1% of failure probability for N1 and N2, and 5% for 3 and 4th components, and 10% for the 5th component, then for this first failure branch, x1 and x2 fail together, so we multiply their failure probabilities. And for this branch, x1 fails, x2 survives, and x5 fails, and x3 fail. And in this way, we can continue this arithmetic to decide the failure probability. And the simplicity of this arithmetic is the advantage of this competition method. And it has also this advantage that there's no need for another branch and bound when the probabilities change. So if we have this different failure probability for N1, then we can simply replace the number and repeat the same arithmetic. So, when we compare the complexity, then now the complexity is, for MCS, the complexity is inversely proportional to the system failure probability, while here we have this, it is proportional to number of branches, which it fairly rapidly increase with the number of rules, but these number of rules are quite well maintained even when the number of components increase, especially when it is a complex network or system. And the probability update requires a new round, while the decomposition methods doesn't require a new round. And another advantage is that the conditional probability of complexity increases with the Monte Carlo simulation. And this is because, for instance, if we want to calculate this component importance measure, which is defined as a conditional probability of this component's failure given a system's failure, and this is because so that we can measure the relevance between these two components, then because of this conditioning, we need to discard all these samples that belong to system survival. So we end up having much less effective number of samples. But in case of decomposition, then we can simply look at to get this intersection probability, which is required to get this conditional probability. Then we can get this intersection by simply looking at the branches where these two failure events occur together, where in this case, it is a case for the three failures for X1, where the X1 fails, while X4 and X5 do not belong to the X1 failure domain. So we can simply get this number as a ratio between the sum of these three branches and the original failure, system failure that we know of. So how can we implement this using this Python and MBNpy package? So if we look at this system, then we have, we first need to define the system event. And then the second input is the probabilities of this component event. So first, in this case, in this system, we have these 4 nodes, and these are simply the coordinates for visualization. And we have these edges that connect these nodes, which are actually used for system function analysis. Then we have this network, we define this system function that given the component state, they assess the system connectivity, and they return system state and the minimal component state if they are available. So in detail, first, given the component state and the edges, we get this, we set up a graph, and we run analysis over the OD pair that we are interested. And if the maximum flow from N1 to N4 is greater than 0, then we conclude that it is system survival. And in this case, we can also return the minimal component state by looking at the path that was used to deliver this maximum, this flow. If this flow is 0, then this means that the 2 nodes are disconnected. So now we have this system failure, we return system failure. And in this case, if we can't decide the minimum component state that leads to this system failure, then we can simply return none. So in this case, you can also return none, but if you can identify the minimal conditions from this component state that leads to this system survival, then the algorithm becomes much more efficient. And the second input that you need to provide is this component probabilities. So for these component probabilities, we can for each of these states, we can specify the probabilities. Then we use this lambda function to generate this system function that accepts only this component state, while other variables are fixed. Then we can put these probabilities and system function to get the branches and rules. And this is how we can get the branches and the number of the 8 rules that we identified before using this MBNpy package. So if we check the rules, then we can find that for the survival rules, it found all the minimum conditions for the system to survive. And the failure rules, we found all these rules that lead to the system's failure. So Then once we are done with the branching, then we need to use this Bayesian network. We can use the other functionalities of this matrix-based MBNpy package to make further inferences. So and this matrix-based Bayesian network is an alternative scheme for alternative data structure for Bayesian network, which is a probabilistic graphical model that is useful for handling complex probabilistic models. So in Bayesian network, the random variables are represented by circular nodes, and the directional dependence between random variables is represented by the directed edges. And it is useful that causal dependence is a subset of directional dependence, so we can use causal dependence to model the relationship between nodes. There's only one constraint in Bayesian network, that it should be directed acyclic graph, because if there is a directed cycles within the graph, then it may create this infinite loop that never converges through inference. And once we are done with setting up the graph, then each node should be quantified by a distribution conditional on parent nodes. So in the case of PX, because it doesn't have any parent node, so it has this marginal distribution. And for Y, because it has a parent node, so it is conditioned on X. And the joint distribution represented by a Bayesian network is simply the product of all the distributions that are assigned to each node. So in the case of our system reliability analysis, then always the problem is with this converging structure between this component event to the system event. And the decomposition method that I just showed you is to quantify the distribution of this system event. So if we have, while without matrix-based Bayesian network or decomposition method, we really have to quantify and store the probabilities of all these exponential number of combinations. But in this case, using this branch and bound, we can quantify the probability, conditional probability of this system event. But by the way, if I'm too fast, stop me, because I'm not sure if I'm explaining enough here. So this the data structure of matrix-based Bayesian network is based on this event matrix and probability matrix that are defined together for each of these variables. So for this system event, each branch constitutes a row. So here we can encode this relationship where if x1 and x2 taking the value of 0, then we are introducing a new state, which is a composite state that can represent both 0 and 1. Then we are encoding this information that if x1 and x2 are taking the value of 0, then x3, x4, and x5 can take any value that is represented by 2, that can be either 0 or 1. And in this case, the system fails. And if we encode this branch, then if x1 take the value of 1, 0, x2 1, and x5 and x3 0, and x4 can take any value, then the system event fails. And we can go on for each of these 10 branches, then we end up having these 10 rows. And because we are dealing with a deterministic system function, we have all probabilities of each of these events as 1. So this is the probability distribution that we just defined for this S. And of course, we need to define the probabilities of all these other components. So if you remember the previous setting, for this x1 and x2, they can take the failure probability by 1% and the survivor state by 99%. And for x4 and x3 and x4, they had this probability of failure as 5%. and for X5, they have 10%. So in matrix-based Bayesian network, we can define these event matrix and probability matrix. Then we can use this quantified matrix by using variable elimination inference, which is also a part of the function in the MBNpy package. So you will be so in the GitHub that we shared you before, there is a tutorial Jupyter notebook that features this tutorial, and this variable elimination is used to infer the marginal distribution of S. So just to give you a brief idea of how this variable elimination works to infer a system definition, system failure probability. So within this Bayesian network, now we need to eliminate all these 5 components, and so that we can have only this S with that whose marginal distribution we are interested in. So if we are given this elimination order from X1 to X5, then in Bayesian network, what happens is we first product this first component that we are going to product, in which case in the graph, we have this combined node, which is represented by this mathematical formulation. And then to remove this one, to marginalize, to remove this one from the graph, we marginalize X1 from this joint graph, in which case now we have this new system node where the uncertainty in the X1 is observed. And if we repeat this process for the rest of these components, then we end up having this system event which has observed all the uncertainties in this component event. And now we have this marginal distribution of the system event where the component, the system failure probability is obtained as around 0.5%. And during the rest of this presentation, I will introduce the how this can be applied to large-scale systems. Although what we'll be looking at during the tutorial sessions are more are in a smaller scale, so that we can have a better idea of how the detailed mechanisms can work. So we had to test this method if it works consistently for large-scale systems with different definitions. So we looked at this EMA benchmark network, where we set this 129 edges as component event. And we wanted to test its applicability for different definitions. So we came up with this system failure event, which is defined as from an origin, the system is regarded as failed if it takes more than twice the usual time to any of the closure airports. And this leads to this 72 system event because we have 24 nodes at -2 airport nodes. And we performed approximate inference, which I didn't explain in this presentation, but we can terminate the branch and bound, the decomposition, when if the bound width is narrow enough or narrow enough. And this is because the enormous number of branches might exist for a system event, but usually a handful of them have a high enough probabilities to affect the system failure probability. And we also terminated the algorithm when it reached 50,000 branches, and in which case we performed MCS on the unspecified branches. So and by performing these MCS only on these unspecified branches, we can lower the required number of MCS significantly. And now the question is, now we have this system event, then for each of these 72 system events, and we have 129 components, and now how we can quantify their system distribution so that we can perform the the system risk assessment. So this is the result where we obtained the system reliability for each origin node, and we mapped out their spatial distribution over the community. And this graph shows the computational costs that were taken for the original case, and the Monte Carlo simulation represented by this yellow bar. And we can see that we can significantly reduce the computation time, especially considering that the y-axis is in log scale. And as mentioned previously, this method is advantageous for update. So when we assume an updated epicenter location, and then we can update the system failure, where system failure map, where now we can find the risk distribution becomes different. And it took only 10 minutes, and this red bar showed the time taken for this update scenario. So in the long term, what we envision through this system risk assessment is these tools can be used in everyday practice of operation, because we all understand that the systems level, systems thinking decisions are now our next step to make our decisions more efficient. So and now this is one of the examples that Dina and I took a couple of years ago, where we analyzed the seismic risk of the urban transportation in Istanbul, Turkey, in a very detailed level possible. And we could find this irregular distribution of the risks around the city. And this is how these tools can be used for detailed and system level risk assessment. So in summary, this session was to introduce the challenge in system risk assessment, especially how we can address the challenge of addressing the exponential costs with computational costs regarding the number of components. And we particularly looked at this decomposition method and how we can apply this decomposition method using MBNpy package. And I wanted to show some large-scale benchmark applications so that you can have the idea that how this can be used for problems with varying scales. Another note is more detailed analysis are possible by adding more nodes in the Bayesian network. So typical practice is when we have this component event and the system event, that we add these hazard nodes to calculate the uncertainty in the hazard scenarios. And we can also add these inspection nodes where we can update the observations on the component events so that we can backpropagate this information to update the system information. And until tomorrow's session, I highly recommend you taking a look at this GitHub files. You can also access it to this through this QR code, where you will find three sets of tutorials. So this first set represents the toy example that we just saw, and the second tutorial, the second set is what we will go over together tomorrow, where we will analyze the risk of school complex as a system of buildings. And there's a third set that we might not go over tomorrow together if there's not enough time, but it shows how we can combine the fragility of bridges together to decide the combined risk of school complex and bridge fragilities. And while you are applying studying these tutorial sets, today or tomorrow before the seminar. If you have any questions, just feel free to drop me an email, and I will try to answer or coordinate the answers and the questions and respond during the tutorial, especially those that appear to be relevant to many of the audience here. And that's it. Thank you. And if you have any questions for me or Asana, just feel free to raise your hand or use the Q&A chat.
There seems to be one
Yes.
question for you, Jiyun.
Right. So this is a really good question. I'm glad that someone asked this. So the dependencies are always an issue. And usually the practice is we first decompose the event space by assuming statistical independence. And this is because during this decomposition algorithm, we repeatedly calculate the joint probability of the component events. But when there is this dependence involved, usually the computation cost is enormous. So the best practice is we decompose the events space by assuming independence, by providing good approximate of the marginal distributions of each component. And later, when we have these branches, then we can compute the probabilities of these branches by considering the dependency between the components. And usually they still give and because this decomposition method is insensitive to changing probabilities, this provides a good workflow. I hope this answers your question. I think you're muted, Asana.
Yeah, I was just saying thanks for answering the question and thanks for the presentation.
Thank you both.
There are more questions.
I think that we don't have any more questions.
Rafa, we cannot hear you very well.
You cannot hear me?
Can everybody else hear Rafa?
No, the volume is very low.
Yeah.
So there is a, there's another question on if the presentations will be shared, and Asana, will they be shared?
It's particularly the system reliability part. Would you like to share? We normally our practice is with the UNESCO Chair webinars and courses, we upload the recording as it is on the website, so people can access the content. We don't normally share the PPTs as such. So, but yeah, there is no problem if somebody would find it useful.
Okay, yeah, then I will upload this presentation on the GitHub, that the link that I shared. Yeah, and I appreciate that it is quite a complex topic. And so that's why I envision that this system level risk assessment sometime become the common practice as fragility analysis, which was also once a complex concept for everyone.
Question for you.
Right, and so I think there's a question for you.
Yeah. So for the cases we presented, it's actually the roof displacement still that is used as the EDP. Yeah, interstory drift ratio can be used, but mostly useful for RC structures with multiple stores, I would assume. Yeah, although we mentioned the IDR, but the used EDPs are roof displacement or the drift.
And regarding Yolanda's question on applying this decomposition method for a frame building structure, So this is a relatively recent development, and in principle, they should be able to be applicable for frame buildings, but I don't have any concrete results yet. But it depends. The applicability should depend on the definition of the failure of frame building, if it is. Yeah, but in principle, they should be applicable, and there are a few studies that apply the different decomposition methods. They often also called bounding methods that were applied to system event structural systems.
If there are no more questions, can we just take a few minutes? Yeah, we still have some time. So can I just present what is the hands-on exercise we're going to discuss tomorrow? With the purpose is that you can have a go at it at your own time, either today or before the session tomorrow. And we can have a discussion on the results afterwards when we meet at 2 o'clock. So let me share the screen. Can you? I hope you're able to see the presentation. So, sorry. The first task is basically to apply the GLOSY taxonomy. So we just very briefly discussed GLOSY and the parameters, the 12 parameters that characterize the seismic performance of structures. So this building you have seen before in one of our examples. But how would you characterize this using a GLOSY taxonomy string? So you are given some visual images. You can look at the attributes of all the 12 parameters and classify them. You're also given some more information. This is to help you with the seismic design level identification. So as I mentioned during the presentation, it's not normally sufficient only to have visual survey to identify the seismic design level. So please have a look at this and try and identify what attribute you would give for each of these 12 parameters, and then you can generate your GLOSY taxonomy string. So the idea of creating this kind of string is that if the string or this type is available on a available fragility database, then you can directly use a fragility function that is available rather than having to again model and analyze your structure from scratch. So this is your first task. The second task is we already saw one example of fragility derivation during the session today. Suppose you are providing a retrofit measure for that RC building. It's basically the same RC building. How would you then derive its fragility functions for the retrofitted case? So for this, you're already given with all the tools that we discussed today, the N2 Excel code and the MATLAB based fragility vulnerability app. So you can have a go at trying to install this tools and running the material, running the analysis for this case. So for this, you're given the retrofitted structure. So as you can see, the GLOSY taxonomy string can be different from the original building, as the typology and the seismic design level and any other features could be different. And this is the new capacity curve, the pushover curve for this particular structure. And you're also given the inputs for your fragility derivation, the EDP damage thresholds, and the loss ratios for the vulnerability derivation. So please use these values. In the zip folder we have already sent you, there is this input file for the capacity, for this capacity curve, which gives you the IM versus or the roof displacement versus base shear coordinate here. So please have a go, and we can come back tomorrow to discuss. And I'm sure you might have questions and more comments to make once you have a trial. So this is the input file that you're given. I hope I'm sharing the screen still. So this is the pushover curve. Please note that there is an update for the threshold values that are given. So use the threshold values that are given in the presentation that I just showed you. So the presentation, I will anyway be sending this file once again after today's session. So we will send all the tools and the GitHub link immediately after today's session. So if anybody has any questions still, we can take them. Else we can close today's session and meet tomorrow at 2 at the same time. Please do come back tomorrow. We are keen to see to get your opinion and get how we can do this illustration tomorrow. So this is more questions about. Okay. Yeah, we have already shared the app, but I'm going to send it again. But for those who have joined late, you should have access to the files by default. It's not licensed or it doesn't require any passwords. Yeah, the link of recordings we will be uploading maybe in 2 days' time after the course. And you can always go to our previous sessions on the fragility vulnerability course, which you might find useful. So with respect to this question on non-structural components, it's not structurally considered in this analysis. So it's basically it's not included in our analysis of numerical analysis following from the capacity curve to the fragility and vulnerability. So this can be, as you mentioned, acceleration sensitive, but this can be a component that can actually have a financial implication as well. So this is basically you can distinguish between a structure that has a non-structural vulnerable component and a structure that doesn't have one. So if you want, you can actually start from scratch and derive the fragility functions, vulnerability functions for both the cases. And also if you're going for what we are currently have shown is a building based fragility and vulnerability, we can also have an approach of component based fragility and vulnerability as provided by some of the guidelines. So in that case, this becomes more relevant. So the alpha and beta values, these are basically your fragility function parameters, the mean and standard deviation of your fragility function. So you derive what we have shown in the N2 method and followed by the EDP to fragility derivation. We would have the piecewise regression to identify the parameters A and B, which are then used to understand or calculate the alpha and beta. So this will be already computed in the tools that are provided. So you will be able to see the alpha and beta once the fragility derivation is run. So I think the questions are answered. Then I think Raphael is answering some of the questions. While you are running the fragility app, please make sure that the LSM input file stays in the same folder. So the input file you will have to open in modify the inputs, provide the IMEDP data, and then close the file. Otherwise, the app won't run because it has to write into the same Excel file.
Right. In terms of Omar's question on the validity of these methods, As far as I know, with building fragilities, there were some discussions that the observations of the building's damage were either non-slight damage or complete collapse, which is against the usual predictions by fragility models. And some of the reasons were attributed to the poor construction, which is another a different type of vulnerability that this conventional fragility analysis assumes. So, but there are these constant efforts to validate this fragility analysis, and these are especially hopeful because of this satellite imagery-based large-scale damage observations these days, where now we can assess the damage, buildings damage at least from the satellite imaging on large scale, and there is an effort to validate it to the with the project analysis. But there's another component that the ground motions are uncertain as well. So this validation is still kind of an ongoing challenge. In terms of system risk models, the validation is almost near, but I can say it is coming. But at the moment, there are no collective data efforts that are trying to validate these system models.
Thank you, everyone. I think we are nearly at the end of the session today. We hope to see you all tomorrow. We will do some hands-on task and also with the system reliability. So we hope to see you all tomorrow again. Thank you for joining, and we hope you enjoy the session.
Yeah, thanks.
Thank you all.